Hey everyone, and welcome back to PrepFusion. I am Anish, and today we will be studying the new chapter, that is the Routh-Hurwitz criterion. Okay, so this chapter will be basically very short, actually not that long. Okay, what we will do in this chapter is find the absolute stability of a closed loop system. So this criterion, right, this will help us finding the stability of a closed loop system. Now, as I told like earlier also, right, for a closed loop system to be stable, what is the condition that needs to happen? Okay, the condition is basically all the poles of my characteristics equation must lie in the left half plane of the S plane, right? For my system to be both stable, all the poles of my characteristics equation, that is the denominator of the closed loop system, must be equals to what? Must be equals to roots must be on the left hand side of the S plane, that is on the left hand side of the j omega axis, right? Okay, so yeah, that is the one condition. But this Routh-Hurwitz criterion will help us find that condition. Is that condition true or not, that all the poles lie on the left hand side or few poles lie on the right hand side also? So this will help us find out that one. So basically, right, this will be the lecture 1. Okay, and in lecture 1, firstly we'll understand what a Hurwitz polynomial is. Then we'll understand like the Routh array and how to construct the Routh array and the Routh-Hurwitz criterion. Okay, what are the conditions, that we'll understand. So first let's understand that the Routh-Hurwitz, like this is not the criterion totally, but first we will just understand what basically the Hurwitz polynomial is. So like the Routh-Hurwitz criterion is a method for determining the continuous system stability for systems with nth order characteristics equation of the form like this. Okay, if they are in the form like this, where xn is the like order and I have like coefficients of each of them. Okay, this is not x, this s, sorry, this should be s. Okay, so if the coefficient, like if the characteristic equation is like this and the coefficients are like this, right, so like I can find the stability, continuous system stability, using this criterion. Okay, so yeah, now a polynomial is said to be Hurwitz if all its roots have negative real parts. That means basically if all the roots lie on the left hand side of the S plane j omega axis, then it will be called Hurwitz. So this is the definition of a Hurwitz polynomial. So if all the roots lie on this area, right, on this area, then it is a Hurwitz polynomial. So let me draw this also so that you guys will understand. So if they lie on this region, right, they will be known as the Hurwitz polynomial. Okay, so now let's find the condition for a polynomial to be Hurwitz. So always my polynomial will be in this form. Okay, so this Routh-Hurwitz, I can find the location of roots for any of the polynomials, right, not for CLTF. CLTF is what we are interested in because we are now studying control systems. So we are interested in the stability of the system. That's why we're interested in the CLTF characteristics equation. But this Routh-Hurwitz can be applied to any polynomials. In your like 11 tools also you found out roots, right, for cubic equations and all those things. From there also you can find the this location of the roots. But the thing to note here is this will help us find the absolute stability, and in later chapters we will study few more other things in frequency response. There we can find the relative stability. We will understand the difference between absolute and relative stability. Okay, so like absolute stability means it will tell us directly that whether my system is stable or not. Okay, and relative, it won't. How it will tell, we'll understand. But for now you understand that this helps us determine the absolute stability of a system. Absolute means it will tell us directly a yes or no answer. We will get an answer as yes or no. Is the system stable? Yes. Okay. Is the system stable? No. Okay, so we will get our answer. Okay, yes or no. Absolute stability. Okay, so yeah, now let's find the condition for Hurwitz polynomial. Let's say I have a order 1 polynomial, then what is the condition for this to be Hurwitz polynomial? So if you observe, right, here all the coefficients must be non-zero, and if my coefficients are of both of them are same sign, then this will be Hurwitz polynomial. Okay, so let me like tell you why. So if n naught so this will be equal to 0, right? A naught s plus a1 should be equal to 0. So that's how we find the roots, right? So what will my s will be equal to minus a1 by a naught. Okay, so for this, like my root should lie on the left half of the s-plane, so this thing should be negative, right? So for this to be negative, what should happen? This a1 and a naught should have same sign, right? If they have same sign, then the signs will get cancelled and I will get, the negative will still remain, so I will get my root as negative. Okay, now if one of them is 0, then what is the problem? If a naught is 0, this is going to infinity, so that is also not the correct solution. And if a1 is 0, then what is happening? If a1 is 0, then my pole will lie at s equals to 0. That is also not stable Bebo stable system, because for a system to Bebo stable, the poles must lie on the left half of the s-plane, not on the j omega axis, basically not on the origin, okay. So yeah, that's why those conditions. So what will be the conditions? Conditions will be, so let me write it here. Conditions will be basically, condition for Hurwitz is my a naught and a1 should not be equals to 0, non-zero. Okay, and both a naught and, okay, where did I go? Okay, this is just suddenly what is happening? Both a naught and e1 should be of same sign. Okay, both a naught and a0 should be of same sign. So yeah, that is basically what my condition for Hurwitz polynomial for a order 1. Okay, order 1. Now let's take another case, but this is order 2. Okay, so but this one I won't prove. Okay, I won't prove, but this one also you can understand. Okay, but I won't prove. The condition for this to be Hurwitz polynomial will be again the same condition as I told earlier also. All the coefficients must be non-zero. Okay, all the coefficients must be non-zero. And what is the other condition? Other condition is all the, okay, I will again copy this one because same sign. Okay, the same condition basically. So like without even calculating these roots, right, we can understand whether they will be on the left hand side of my geometry axis or on the right hand side. So like the main thing is this coefficient, right? We are interested in when these coefficients are real, right? Okay, we're interested in real coefficients. So this a naught, a1, an minus 1, all of them will be real. They will not be complex or imaginary. Okay, so that is also another thing to keep in mind. Okay, so like yeah, these are the conditions for second order and first order system. So yeah, let me like put this in a cloud thing. Okay, so like what is the main thing here is we are not interested in the exact location of the roots. Okay, we are not interested in finding the exact location of the roots. So as we are interested in just understanding the stability of the system, we just need to know in which region does the roots lie. So what is the, like, another key, what is point to note here is, that's why this Routh Hurwitz is very very useful. Okay, as we are interested in only knowing about the stability of the CLT, right? Knowing only stability of CLTF, only knowing about the stability of the CLTF, then only, so hence understanding the distribution of root distribution of poles is enough. Okay, understanding the distribution of poles is enough, right? That's why we're only interested in the distribution, as told here also, like here also, right? Here. Okay, so yeah, this is what thing that I wanted to like give you. Okay, wanted to tell you, right? So now, what are the condition for a polynomial of Hurwitz? So this is the one of the condition. If for polynomials of order below 3, okay, below 3, basically 0, 1 and 2, 0 polynomial is nothing. So first order polynomial and second order polynomial, the necessary and sufficient condition for them to be Hurwitz is that all coefficient must be non-zero and of same sign. Okay, so this is for the order below 3. So now these are few polynomials, right? These are few polynomials. Now what I want you to do is, obviously you can find it out from here. Okay, you can find out the roots from here, like just by simply doing in hand calculation. You can search in Google that solve for x calculator. There you will put the coefficients, and there you will see the roots of each of these 3, right? And what you will check is, if I take the first one, okay, so what is this question asking us? Check whether the following polynomial is a Hurwitz polynomial or not. So what is defined as Hurwitz polynomial? The poles, the real parts of the poles should lie on the left hand side of the geometric axis of the explain, right? So they should be negative, basically poles should be negative. So this is deleted now. So we copy this here, paste this. So this is the first case, right? So if you check this one, I've already checked this one in like online calculator, that the poles of this one, right, will be there will be 2 complex conjugate poles and 1 real negative pole. So poles complex conjugate poles and basically 1 negative real pole, right? 1 negative real pole. Okay, so 2 complex conjugate pole and 1 negative real pole. So we have 2 poles, 3 poles, and all of them are lying in the left hand side of the geometric axis. So what does this mean? This means that system is like, this is Hurwitz, right? Hurwitz polynomial. This means this is Hurwitz polynomial. Now what about the second case? So about the second case, right, what is my basically equation? So this is my equation, right? Now if you put in the computer this coefficients, what you will see, what I just did, I just swapped this. Here I had 3 and 1, right? I just swapped this 3 and 1. Okay, I just swapped this 3 and 1. So what I will see, I will see that my location of the poles, distribution of the poles has changed drastically. So what has happened? I still have 1 negative real pole. Okay, still have like this. I should write as location of poles. Location of poles. So yeah, still have I still have basically let me write here. Look, you can copy this one. What are my location poles in this case? In this case, right, I will still have 1 negative real root. So I will copy this one again. So 1 negative real pole. Okay, but what will happen to my complex conjugate poles? So my complex conjugate poles from left hand side will go to right hand side. They will be still complex conjugate, but they will go to right hand side. So I will have complex. Okay, so I shouldn't write here 2 actually. Okay, sorry. Oh, no, shouldn't write here 2 because this is already complex concept. These are already 2 poles, right? Else you get confused. So that you know, right? Whatever the maximum order of my this equation is, that is the number of roots. So sorry for writing 2 here. That will be just some silly mistake. So yeah, I will still have complex conjugate poles. Complex conjugate pole on the, now what is the location distribution? It is on the right half plane, right? Right half plane. It is on the right half plane, right? So is this Hurwitz? No, right? Because 2 poles are lying on the right half plane. The system has become unstable anyways. But like Hurwitz criteria is all the real parts should be on the left hand plane, right? So this is not Hurwitz. Okay, this is not Hurwitz polynomial basically. Okay, this is not Hurwitz. Okay, so let's go to the third case. P3, right? Just go to the third case. So this is P3. What is happening? So basically, right, what is what was the first condition? First condition was all my coefficients should be non-zero and they should be of same sign. That is like what I forgot to told you is that basically these are the third order systems, right? These are the third order systems. So here you can't simply apply this condition. That's what I was coming to add, because here, right, so like this was the condition as I told, right? This is for polynomials of order 3 and below, right? 3 and below. So here if my order is 3 and below, then the necessary and sufficient condition is this one. Okay, this one. But for order 3 and above, okay, for order 3 and above, then my sufficient condition will change. This is still the necessary condition, that all my coefficients must be non-zero and of same sign. Okay, so these follow that necessary condition, but the difference is something else that we'll understand a bit later, right? But here this is not even following the necessary condition. Okay, hence by just seeing the polynomial, I can tell that this won't be Hurwitz. Why? Because the coefficient is negative, like there is basically sign change of the coefficient. But here, right, the necessary condition should be they should be same sign. Even though this is for order 2, I will later on we will see that for order 3 this is the necessary condition, but this is not the sufficient. I hope you understand, right? Necessary condition means it has to satisfy that condition for us to get an Hurwitz polynomial. But it is not true that only if we satisfy only that condition, it will be always Hurwitz. No, I have to satisfy other condition also. Okay, so but it is one necessary one, it has to satisfy that condition also. So yeah, so here it is not satisfying. So by just seeing the coefficient, like just seeing the coefficient, I can say not Hurwitz, right? Slowly you just watch along the lecture and you will understand. Okay, not Hurwitz. Okay, so yeah, this was for the 3 case because there is a sign change. Now let's check for polynomials of order 3 and above, right? So for polynomials of order 3 and more, a necessary condition for them to be Hurwitz is that all coefficients must be non-zero and of the same sign. So all the coefficients must be of non-zero and they should be of same sign. So this was a previous necessary and sufficient condition for order 2 and below, but here it is just the necessary condition, but this is not sufficient, right? This is not sufficient. Okay, so then what is sufficiency? For sufficiency we have to construct the Routh array. Okay, so for sufficiency we have to construct Routh array. Right? So that is for the sufficiency. Now what is Routh array? That is exactly what we'll understand now. So we have consider a characteristic equation like this one, right? Polynomial equation like this. Okay, that it has coefficients as a0 s to the power 6, a1 s to the power 5, and so on. Okay, so on. And now how will we will we write the Routh array basically? So what we'll do is, first we'll write all the powers of s in one column as a column. So first what we'll do, write all the powers in one column. Then what we'll do, I will write the first two rows, right? First two rows of the arrays as the coefficients of the terms. How I will write that, I'll show in the next slide. So write the coefficients of my equation. Okay. So yeah, this is basically what I will do. So here, this is the Routh table, or you can say Routh array or whatever. Okay, so this is the column thing that I wrote s to the power 6. So starting with the highest power to the lowest power. What is the lowest power? It is not s to the power 1. S to the power 0 is also there, right? So don't forget that. Okay, now how do I write this one? So what I do is, first I write the coefficient of s to the power 6, which is a0. Okay, then I skip this one. Okay, then I skip this one, then I write this one. So this is a2, right? So I write a2 here, then a4 and a6. Okay, I skip one. Okay, I skip each one of them. Okay, and that's how I complete the first row. In the second row, how I will complete, obviously the skipped portions, right? Skipped coefficients that I will write here in this second row, right? So basically I will have a1, a3, a5, and this will, like, whichever is left. Okay, and I don't have anything to fill it up, that I'll fill it with 0, or you can say null, right? Nullity. So this was the first row, then I skipped this one, so this will be in the second row. Then I took this one for the first row, then I skipped this one, so this will be in the second row. Then I took this one for the first row, then I skipped this one, this will be the second row, and this is will be again in the first row. So yeah, I wrote the two rows, right, of the Routh table. That is done. Now next, what I need to do next is, I have to start calculating. So you might ask, sir, what are these coefficients you wrote? Like, these are just unknown for now. Okay, but what are the values of the coefficient? So I wrote these two rows, right? Now what I'll do to compute this b1 coefficient, right? To compute this b1 coefficient, I need to do some mathematical operation. Basically the column, basically the row above this, element above this will be a1. So I will take a1 times a2, then I will subtract this diagonal element a0 minus a0 times a3, and then again I will divide by this element above this b1. Okay, so what will my b1 equals to? My b1 will be equals to a1 into a2 minus a0 into a3 minus a0 into a3 divided by a1 itself, right? Divided by a1. Okay, that is how I compute my each elements of Routh table, right? Okay, now what will my b2? Semi. So for b2, right, what you will do, but this element will still be there. Okay, the thing I that I forgot to tell you is, like, this element will for b2, right? b2, what you will do, like, this element will still be there. So you will take this element and the columns of this element. Okay, so what I did over here is, I took the first element over here, and then I took the columns of this element. Okay, then for this element also, what I'll do, I will always take the first this column, right? This column I will always take the first column above it, two rows. So okay, let me first write it, then I will explain. Okay, because it is getting difficult for me to explain. So what will my b2 is simply this a1 times a4 minus a0 times a3 divided by a1 itself, right? Divided by a1 itself. And what is my b3 equals to, so my b3 equals to simply a1 times a6 minus a0 into 0. So like, okay, I will explain. Minus a0 into 0, so let me write first, then I will explain, right? And this is divided by simply a1. Okay, so this is my b3 equals to, which gets equals to a6. Okay, now let me explain. What did I do? b1, I hope you understood what I did. Basically I took this a1 times a2, then subtracted a0 times a3, right? a0 times a3, and then what I did, I divided by a1 itself. Right? So yeah, that is what I did. Now for b2, what I do, for b2 I again took these two elements, but I multiplied a1 this time with a4, right? The column after this. So this is the diagonal multiplication. Okay, so I multiplied by a1 times a4, then what I did, I subtracted, again I took this one, okay, a0 minus a5. So I am taking this column and this column. Okay, when I'm picking this element, I am taking this column and this column. When I'm taking this element, I am taking this column and this column. And when I will be calculating this element, which columns I will take? I will take this column and this column. So first column will always be there, okay, but this will keep on changing its column, right? Okay, so the second column basically. So I hope you got it. Now what is the point to note here is these calculations I hope you got. So I will always take the first column and always divide by the first column of the element, right? This one I will always divide. So this is the diagonal multiplication. So this is the diagonal multiplication, then I subtract with this one, then I divide by a1, right? So divide by a1 will always be there. So another thing to notice here is the coefficient b3, right, is directly a6, right? Directly a6. So whenever there is a like this second column, the element just above this one is 0, okay, is 0, then the element above this one will come over here. Okay, why? Because I will multiply a0 with 0 this one, and then I will divide by this element, the multiplication of this one and this one. So the multiplication of this one and this one I am dividing by simply a1, so dividing by the same element itself. So only I will get back my a6. Okay, so this is very helpful while computing the Routh array. We will understand slowly, we will solve questions there also. We will solve a lot of questions there. We will understand the Routh array. Okay, this was for this row. Now let's calculate for another element, that is the c1. There also you will get your concept very clear. So if I calculate for the coefficient of c1, what do you get? c1 equals to this. Now I will choose these two, right? I will choose always the two rows above this one. Okay, two rows above this one. So these two I will choose, and what will be the second column? Second column will be for c1 will be these two, right? These two. Okay, so now tell me what will be the basically diagonal multiplication. It will be b1 times a3 minus a1 times b2, right? So this will be my the numerator. Okay, numerator of c1. So numerator of c1 will be b1 times a3 minus a1 times b2. Okay, minus a1 times b2. Now what will be like, what will I divide it with? I will divide it with this above element, right? This is b1, so I will divide it with b1. Okay, I will divide it with b1. Okay, so I hope you got the crux of this, right? I hope you got the crux of this, that what I do is basically take the two rows above this, and the first column will always be present. Okay, first column will always be present, and the second column keeps on changing its position. For this c1, this will be my second column. For this c2, this will be my third column. Okay, so yeah, that is what I got. Now let me do another computation. From there also you will understand that. Let's say I want to calculate this e1, right? I want to calculate this e1. So for this e1, what will be my elements? This will be my first column and this will be my second column. Okay, I hope you got it. Okay, now yeah, that is basically it. Now let's say I want to calculate this d2. Oh, sorry, not this. Okay, yeah, like, sorry, I should have written it here f1 actually, but I got d2 here. Tell me how I got d2 here. I got d2 here because I have a 0 over here, right? The second column, the element just above it is 0. So what happens? I multiply e1 by d2, then I subtract d1 into 0. So this becomes 0 only. So e1 into d2 divided by e1. so it becomes d2 only, so I get d2 here only. So yeah, that is the trick basically. So you don't need to compute this one, even though if you want to compute, you can always compute, but if you don't compute, right, you can directly place this d2 over here. This is the I mean, not the, this is a shortcut basically. Okay, so yeah, so I will write this here. So the procedure basically, write first, okay, let me do this in smaller thickness. Write first 2 rows, and here we have to compute the rest. Here we have to compute the rest. Okay, so yeah, this is basically what we do. And diagonal multiplication, I hope you got right, and then we divide by this term, whatever is just above it. Okay, basically the first column. So this also you have to understand that there will be a gap of 1. Okay, so all these things you have to take care for a Routh table. So this is just a Routh table. Don't worry if you don't understand, because we'll solve so many questions, this will get into your head. This is not that big of a deal to understand, right? So yeah, so what happens is, after this, what do you do? After computing the Routh array table, okay, Routh array or table, we just look at the first column, because first column is very important. Okay, so after computing Routh table, we look at the first column, basically first column of the table. Okay, but you might ask why. To look at the sign changes basically. So this, right, all this will come out to be something, some numerical values, right? Now if there are sign changes, what do you mean by sign changes? If let's say these are positive and this b1 coefficient comes out to be negative, if there is sign change, then my poles will lie on the right hand side. My poles will lie on the right hand side of the S-plane. Okay, if there are sign changes, basically this is positive and this is negative, so my poles will lie on the right hand side. Now the number of sign changes will define how many poles lie on the right hand side. Okay, and the remaining poles will either lie on the left hand side or on the imaginary axis. It will depend. Okay, but number of sign changes will perfectly define how many poles lie on the right hand side of the S-plane. So then sign changes. Okay, number of sign changes of the first row. Okay, so let me put a few examples and then you will understand. So let's say I take example that this is my first row, right? Plus 1 plus, not the first row, sorry, first column, then I get -2, then again I get -3. Okay, so how many sign changes are there in this first column of the Routh table? So what I can observe from here is number of sign changes is what? Only 1, right? 1. Why? This is positive, this, so I'm going from here to here, this is positive, no sign change. I'm going from here to here, positive to negative I'm going, so this is 1 sign change. Then I'm going from here to here, this is no sign change, because this is negative and still this is negative. So how many total number of sign changes I have? I have 1 sign change, right? So 1 sign change. Okay, so this is basically after computation. Obviously we'll do few examples, from there you will understand. So this is the after computation of the Routh table. So this is the first column basically, that is what I'm representing here. So let me take another example. second example if I take, right? So now if I have, let's say my columns are like this one, +2 -2 +1 and +3. okay, my columns are like this one, elements are like this one, sorry. So how many number of sign changes are there? So from, if I go from here to here, I see one sign change. If I go from here to here, I see another sign change, right? Because this is going from positive to negative, then I'm going from negative to positive. So I have two sign changes, right? Two sign changes. Now if I go from here to here, I have no sign changes. These are positive only. So how many sign changes I have? I have two sign changes. Okay, so I have two sign changes. Now like let's come to the actual definition of the Routh stability criterion. This is the basic definition, right? So what is the definition? For polynomials of any order, okay, a necessary condition for them to be Hurwitz is that all coefficient must be non-zero and of same sign. So this is the necessary condition, not sufficient, right? Okay, so that is the main thing. This is the necessary condition. So this has to satisfy, at least for polynomial of any order, at least this has to satisfy, this condition has to satisfy. If this condition isn't satisfied at the first place, then I can blatantly say that my polynomial is not Hurwitz, and I can, if it is a polynomial of characteristic equation, if it relates a polynomial characteristic equation, I can blatantly say that my poles lie on the right hand side, and I can say this system is not stable. Okay, so by just seeing the coefficients of my polynomial, I can directly say that they are not stable. The system is not stable because they are not satisfying the necessary condition. This is necessary but not sufficient. If it satisfies the condition, then I can surely say that it will be stable. I have to check further. So this is not sufficient. Okay, I will write here. Not sufficient. Check further. Not sufficient. Check further. Okay. Now, what is the sufficient condition? So the sufficient condition is coming. The number of sign changes in the first column of Routh's array should be 0. Okay, this is the sufficient condition. So also like this should be 0, and also all the first column of all the elements of the first column of the Routh's array should be non-zero. Okay, that I like this one I just explained, that number of sign changes should be 0. If they are 0, then my system will be stable. Basically the roots of the characteristics equation will lie on the left hand side of the S-plane. Okay, they will not lie on the right hand side of the S-plane. So what I can say is these two are sufficient condition, right? And also what is another condition? That the first column, the elements of the first column should not have any like element equals to 0. They should be all be non-zero, and the number of sign changes should be equals to 0. Okay, so yeah, these two are my sufficient condition. Basically if I check these two conditions, then I will be completely sure. I don't have to check this one. Okay, obviously just by seeing the like equation you can say okay, but if you just check these two conditions, you are good to go. Okay, you are good to go. If these two conditions are satisfied, then your polynomial will be stable. Basically your system will be stable. So this is the sufficient condition. Okay, so yeah, so these two are sufficient. So just keep this in mind. Okay, these are theory only. Okay, this first lecture will be theory only. Okay, this first two lectures will be theory only. In the third lecture will be mainly questions. Okay, so yeah, few key points are here. So what is the key point? For my closed loop system to be stable, all the elements of the first column of the Routh table must be same sign. Okay, this was the stability criteria that it was saying. So this is valid for any polynomial. But what we're interested in? We're interested in the characteristics equation, okay, of our system. So this is talking about the stability of my system. Okay, previous it was globally, right? Routh stability just gave one statement like about the location of the poles, right, about the distribution of the poles. But this is the important part to us, is that as I told earlier also, they must be of the same sign and they must be non-zero, right? Okay, For my closed system, all the elements of the first column of the Routh array must be of same sign. The number of sign changes of the first column of the Routh array represent the number of roots of my polynomial in the right half plane. So this is also another point. So the number of sign changes, right? Here I have 2 sign changes. Then my number of poles at the right hand side will be 2, right? 2. Okay. Here there is 1 sign change. So my number of poles at the right hand side will be only 1. Okay. So yeah, that is the thing what the number of sign changes in the first column represent. Okay. So this is also another important point. Keep this in mind. So from this I can understand how many poles lie in the right half plane, but just keep in mind I won't be able to tell how many poles lie in the left half plane. Okay, because they may lie on the imaginary axis also and on the left half plane also of the geometric axis. So they may lie on the imaginary axis also on the left half plane. So how to identify, we'll see when we will do examples. We'll see. Now all the coefficients of my characteristics equation must be real. So this is basically for which this criteria is valid. So this is already I am saying it that all my coefficients should be real. In exam the coefficient will be real, no worries. Okay, so this is just to let you know that yes, all the coefficients of my polynomial or my characteristics equation must be real. Okay, if my characteristics equation only consists of even power of s, then this represents the presence of pole on the imaginary axis. So let me give you an example. So let's say I have this polynomial, right? S squared plus 1. Okay, this consists of only even power of s. How? 2 is even and this is s to the power 0. Okay, then my polynomial consists coefficients of only even power, right? So if I solve this, what do I get? I get s equals to plus minus j. So what does this mean? This means my poles are at the imaginary axis. Okay, so now if let's take another example. This is s to the power 4 plus s to the power square plus 1. This is equals to 0. Now what is what are the roots of this one? What I can do, I can simply convert. Okay, let me solve this a bit easier. Let me do this 2 ways. Okay, then this will be easier for me to solve, right? So what I can do, I can convert my s to the power 4 equals to x, right? So not x, I can convert my s square equals to x. Then this will become a quadratic equation. So s to the power 4 equals to, let's say x square, right? Okay, or what I can write is basically s square equals to x. Okay, so I will convert this in this equation. This will become x square plus 2x plus 1 equals to 0. So this will become x plus 1 whole square equal to 0. So what is my x equals to? So I have 2 roots, right? This is x plus 1 whole square. So I will get 2 negative repeated roots for x, not for s. Okay, but I am interested in s, right? Not for x. So x will be equals to minus 1 comma minus 1. Okay, now but this is my x. I need to find my s, right? As I told you earlier also, the number of roots of an equation will depend on the highest power. I should have 4 roots, but this x has 2 roots because this x was equals to s square. Okay, that's why. So now this was a second order. I converted this 4th order equation to a second order equation, right? So now what I'll do, I will simply write this here that my s square equals to minus 1 comma minus 1. Now I will take the square root of this one. So if I take the square root of this one, what will happen? I will get 4 roots. How? Because this will be something like this, right? S equals to plus minus under root minus 1 plus minus under root minus 1. This represents they are repeated, but it's okay because here also they are repeated, right? So this represents they are repeated. I got 4 roots of plus minus under root minus 1 and plus minus under root minus 1. So what does under root minus 1 represent? I hope you know that, right? It is a complex number. It is the j, right? So it lies on the imaginary axis. Okay, and this also lies on the imaginary axis. Again we see they are repeated and they are lying on the imaginary axis. So if my characteristics equation consists of even powers of s, right? Only even powers of s, then I will always get imaginary roots, right? That will lie on the imaginary axis. I will always get poles on the imaginary axis. So yeah, that is basically it. Now if my characteristics equation has its constant term equals to 0, then at least I will have a root at the origin. At the origin means s equals to 0. So let's take that example also. So let's say I have s square plus s and this is 0, right? Equals to 0. So my constant term, that is the s to the power 0 term, coefficient is 0 for that one. So is 0 a root for this one? It is, right? It is, because if I take common s over here, it will be s plus 1 into 0 equals 0. So what is the one root? One root is s equals to 0, another root is s equals to minus 1. So yeah, from here we can understand, if my constant term is 0, then I will get a root at s equal to 0. So these things are important while solving in the Routh-Hurwitz table, right? All, because that's why I am telling this from now only. Okay, from now only, later this will come in handy. So keep this in mind, and also I am doing examples so that this gets in your head, right? So what is the next key point? Next key point is, my Routh-Hurwitz criterion is not applicable for sine, cosine and exponential function, because okay, this has become sorry, because my function, basically it will be my function, because function, these functions, function contains infinite, okay, why is this happening regularly? These functions, okay, where did I go? These functions contains infinite number of terms. Okay, so what do I mean by infinite number of terms? So I hope you know I can write my exponential. Okay, so let me show you one example, that my exponential e to the power x, can I break, how can I break it down? So it can be it can be broken down into a series format. So it will be 1 minus x, then what happens? It becomes plus, right? Why? Because it is basically, the actual series is basically like this one. So it is plus into minus x divided by 1 factorial, okay, plus into minus x whole square divided by 2 factorial, then plus into minus x whole cube divided by 3 factorial, and it will go on, right? Go on. So again, if I rewrite this, simplify this one, this will become 1 minus x plus x square divided by 2 minus x cube divided by 3 factorial, okay, and so on and so on and so on, right, and so on. Okay, but so what we are seeing, this is a infinite polynomial terms, right? Infinite number of coefficients are there. So this is a problem, right? I can't solve it in Routh. How many will I write? Okay, that's why what you do, we apply the linear approximation. That's why it is told here that for analysis of these functions we'll use linear approximation. What do you do? We assume that this x, right, is very small number, that this e to the power x, sorry, this will be minus x, sorry, I'm so sorry, okay, this will be minus x, okay. So this e to the power minus, for e to the power x it was this one, for e to the power minus x, basically x is replaced by minus x everywhere. So I'm sorry if you were just watching the video and just like very confused what is happening. So yeah, this, what I do is assume my x is really small. If my x is really small, then what will my x square be? So let's say your x is 0.1, okay, then what is your x square? X square is 0.01, it is very small. What is my x cube? X cube is 0.001, okay, again very small, right? So it is keeping on reducing, it is reducing further, right? So what is happening with the increase in power, my x square, x cube, all the higher order terms are reducing, so they are insignificant in this, right? So if I replace this one, only this will be the significant term, all this will be insignificant, right? Because this is the dominant one. So my final result will mainly depend on this one instead of all of this one, right? So what I can do, I can apply linear approximation. So basically my e raised to power minus st will be approximated. So okay, I will not st, I will write st later. So my e raised to power minus x will be approximated as 1 minus x. What is the condition? Condition is x is small, x is small. So this is my condition. So in like control system, we don't have e raised to power x. We what do we have? We have that I was writing just, we have e raised to power minus st. So if you have e raised to power minus st, then I can approximate it as 1 minus st, right? 1 minus st. And what is this called? This is known as the linear approximation. This is known as a linear approximation basically. Okay, so now I have got a few questions. Okay, so I will give you homework these questions and you will solve this. I will solve this in the next lecture. So we have to compute the Routh table for the following and check for stability, right? Compute the Routh table for the following polynomials and check for stability. Stability, like assume that these are my closed loop characteristics equation. So I will write, if these polynomials are characteristics equation of CLTF basically. Okay, so yeah, then tell me out of this one which one will stable. So basically these two are same example only. I told you that root side solution, but you compute the Routh table and practice by yourself, then we'll solve this in the next lecture. Yeah, thank you for watching.